The alpha carbon is hiding in the back here. That's the number 2 carbon. And this carbon here is number 3 in the chain. And this is our beta 2 carbon right here. Okay, so that's our reference point. And we can do lots of rotations about these things, but just by dumb luck, let's consider this bromine at the alpha position and this hydrogen at the beta 2 position. And what's the orientation of these two atoms? The words we could use are anti-periplanar, syn-periplanar, eclipsed, staggered, 60 degrees, 90 degrees, 180 degrees. Just write something that comes to mind in the chat message for us here. These anti-periplanar, syn-periplanar, eclipsed, staggered, 180 degrees, 0 degrees, 90 degrees. What do they look like to you from my diagram here? And I'm talking about this bromine and this hydrogen here on different atoms. Right? These are anti-periplanar, that's the correct word for them. Yeah. And the orientation for these two things, if you build them, or even looking here, they're 180 degrees apart from one another. Okay? These two atoms here, there's another beta hydrogen. So here's an interesting facet of this. This particular beta 2 position has 2 beta hydrogens, and I have one finger on each one of them. This one is anti-periplanar, 180 degrees from bromine, and reactive. What's the bond angle from this hydrogen here? I want an angle, a degree angle measurement between here and here, from this beta hydrogen and this bromine. What's that bond angle? You should know it from your work with Newman projections only like 4 weeks ago. You already forget? It's only 4 weeks back. Yeah, 60. Thank you, people. This is rapid fire here. Good. You don't have dementia. Neither do I. I remember too. These are 60 degrees apart from one another. So this one is actually unreactive. You could actually write in your notes that this is reactive and this is unreactive. I'm not going to write it on this diagram because I just don't want to make it too confusing for everyone. But I'm leaving right now. You could write next to this hydrogen here in pencil or somewhere else, this beta hydrogen is unreactive because it's 60 degrees disposed to bromine. This hydrogen is reactive. It's in the anti-periplanar 180 degree conformation. So this difference between these two, why this one doesn't work and this one does work, is very complicated. It's a very high level of molecular orbital theory. This bond breaks and the electrons have to fall kind of into the backside of the carbon-bromine bond, and these electrons can't make it there. We don't need to go to that level of understanding, but we can say that this is anti-periplanar and 180 degrees reactive. 60 degrees, not anti-periplanar. 60 degrees, not syn-periplanar, unreactive. Okay, so let's drop base molecule right below this. Let's use ethoxide. Okay. It's kind of difficult to draw the mechanism on a Newman projection. So I'm not going to draw it. I'm not going to draw it per se, but we're going to have to think about this for a little bit. This is going to attack this proton. And this proton is going to get plucked off. It's going to disappear. These electrons from beta 2 are going to fall to the alpha position, which is kind of this bond that's in the plane of the board here. There's 2 carbon atoms here, 3 and 2 behind it, or beta 2 and alpha behind it. We can't really see it. As this reacts with this, these electrons in this bond break, and they start forming a double bond right down the middle of this molecule, and then bromide leaves. So at the end, these two things are going to get kind of plucked off. Okay? This is sp3 hybridized. It's going to become sp2 hybridized as it becomes an alkene. So it's tetrahedral now. But as these two groups get plucked off and we start forming a double bond in the middle, this whole molecule is going to get kind of paninied. It's going to get sandwiched right together. And then we're going to flip it over. I want you to look at this arrangement, and I want you to think, this attacks here. These start forming a double bond. This whole molecule starts flattening out, and bromide leaves. What's the alkene that you would form from the way all these atoms are lined up? Are you going to form the trans-alkene, trans-2-butene, or cis-2-butene? Just try and draw what you think happens here. It's kind of in the wrong orientation, so you're going to have to flatten this molecule, put the double bond in it, maybe flip it over, sandwich it over. Write it right here, and then in the comments, just write whether it's a trans or cis-2-butene. You don't have to write that whole word out, but you can just draw what you think it is, and then just type in the comments whether you think it's trans or cis, right? These two groups get plucked off. One comes from the base, bromide leaves, we start forming a double bond quickly. You think these methyl groups are going to be on the same side or opposite sides, trans or cis. Maybe you can't do this, but just try anyway. Try to draw whether you think this is the trans 2-butene or the cis 2-butene. It's okay if you get it wrong. But right now you should be drawing something or imagining something. Double bond will be right down the middle here. This will be gone. This will be gone. Double bond will be right down the middle. So if we were to take that double bond and flip this molecule down, what's it going to look like, cis or trans? You guys write in the comments what you think. I'll take a snooze until you write something. Trans. Thanks, Anna. Trans. Thanks, you guys. Yeah, so this particular arrangement, this hydrogen will be gone. So maybe we have CH3 here, H here. And maybe this is carbon 3 in my mind, or beta. Let's just call it carbon 3 right now. So we have methyl and a hydrogen. And then in the back here, you can see these two guys are kind of close. And then the top here, we'd have that. Okay, so it's okay if you didn't see this or can't see this, right, just yet. But if you build it, draw the Newman projection, and just imagine what's happening. The textbook also has a good example of this, and I believe the preview video had a good example of this too, but if not, work through this until you get an understanding. So this particular conformation helps us explain the trans. Let's actually now do the cis explanation, okay? I would like to go right up here, but I think that's probably a little unfair to everyone. I'm just going to keep writing below this. And it might be a little more challenging than I imagine here. So what I'm going to do with this now is I'm going to rotate it 120 degrees. Okay? I'm going to take this Newman projection, I'm going to rotate it 120 degrees clockwise. The reason I'm going to do that is I want to actually put this hydrogen in this position. So this hydrogen, when it lined up anti, this is the preferred conformation, it gave us trans stereochemistry. Let's actually draw the Newman projection. Why don't you actually practice drawing this? I'm just going to leave 30 seconds for you to jump ahead. I'm just going to draw the skeleton here. I'm going to leave the back carbon alone. I'm going to rotate the front carbon 120 degrees clockwise. What's the picture you get from that? Okay? Fill in these front 3 spots if we rotate this front one 120 degrees. If I rotate it 60 degrees, it's going to be eclipsed, and eclipsed isn't going to work for us. I want it staggered. I want a nice hydrogen in this anti position. If you rotate this 120 degrees, we should have this picture. Our former hydrogen that was in a box is now here. Our methyl group came down 120 degrees. This hydrogen that didn't have a box on it is now over here. Let's just put a circle on it. It's different than the box one, but again, we see it in the perfect anti-periplanar 180 degree conformation. Let's imagine base now coming in reacting with this. Bromide leaving, and imagine a double bond forming right down the middle of this. Imagine a double bond forming right down here as we take these 2 pieces off. You can almost see the double bond forming right in the middle of this Newman projection. These are on different carbons, by the way. This is carbon 1, 2, 3, and 4. So there's 2 carbons in the middle. And if this conformation led to an alkene, 2 methyl groups would end up on the same side. And we would get the cis alkene from these 2 different conformations. So in this grand scheme of things, I'll put this right back in just 1 second. We make 20% of this and about 80% of these. These are more favored by Zaitsev's rule. They're more energetically stable. And Zaitsev's rule also said that transalkenes were more stable than cis, or more likely to form than cis. Let's look at these two conformations again that we have drawn here. These are the two that are most reactive, the ones where hydrogen is 180 degrees apart. This one, if these disappear, we form a double bond here. The two methyl groups will be on opposite sides of the double bond. This is trans. If we do that same exercise here, pluck off these two groups, double bond will start forming. These two carbons will be on the same side, and they're cis. Let's look at these two conformations and try to make an educated guess about which one is more stable. Let's take it all the way back to Newman projection. One of these two conformations is more stable than the other one. One of them is less stable. One of them is more stable and leads to a more stable, higher formed product, the trans disubstituted. One of these conformations is less stable, leading to a disubstituted cis conformation. See if you can compare these two things and figure out why one is more stable or less stable than the other. These are in the staggered conformation, so they don't have eclipsed interactions. But in the staggered conformation, there was a special type of energetic penalty you encountered with Dr. Marinas. When two large groups are 60 degrees apart from one another, we call that a gauche interaction. A gauche interaction. We could look these up in a table, but there's a small penalty for bringing a methyl group and a bromine together. I kind of just draw this little penalty like these two things. It's like two clouds of electrons bumping. We could actually look that up in a table, and it has some small penalty. It's very, very small compared to eclipsed interactions. And down in this conformation, we have that same exact penalty. So these two have a methyl-bromine gauche penalty. But this conformation also has the methyl-methyl gauche, which you're used to. This is, I think, 0.9 kcals per mole. I even remember that, even though I didn't teach it to you this semester. So this has the same methyl-bromine gauche penalty, but an additional methyl-methyl gauche penalty. So these two conformations, this one actually is more stable. Since these are freely rotating, we'll be stuck on this conformation more than this one because this is energetically a little bit higher in energy. So this particular relationship from Newman projections translates all the way into how this is the most major product, next less major, and then Zaitsev's rule says mono-substituted are less favored than the following. But these two and their relative predominance being this is the most favored in our Zaitsev's trend out of the three products we're making, the second most favored, can actually be readily seen from these two Newman projections and the conformations that they originate from. So this is kind of high-level thinking, everyone. I don't want you to panic, okay? I want you to practice these Newman projections for this very simple example like we've done. I do want you to master being able to look at a substrate, having base, and being able to do mechanisms without Newmans, like we did previously. I want you to be able to predict all unique products from a substrate, just like we're doing here. This I want you to practice, but if it's really struggling, if you're really struggling with it, please really emphasize the prior work that we've done on this particular topic, and don't unnecessarily punish yourself on this at the expense of learning the basics, which are very, very important for your success on Thursday. Again, what I mean by basics, take a reaction, the same molecule, we identify all beta positions, we expand those beta positions, you can do the mechanism, you can predict the product. This is the most important thing you have to work on. If you've mastered that, then you move on to deeper understanding using these Newman projection type diagrams. We'll do one more Newman projection diagram. Maybe what I'll do today is I'll set the problem up. It'll give us like 5-7 minute break, whatever we have, and then when I come back, I'll expect answers from you, what you worked on. So again, you'll have time to use the restroom, get some water, do whatever it is you like to do with 5 or 10 minutes of free time, stretch your fingers or review notes for questions. But I'll leave a little problem here for us to work on as well. I'm going to draw this a little bit differently. I'm going to draw a molecule that can undergo E2 reaction. I'll give you time to catch up. with my drawing. I know my drawing's a little different than usual right now. That is a little bit of a different type of drawing. There's one alpha position. There's two beta positions. But this one is the only one that has a hydrogen at this particular location. Okay, so those are the key bits. And we're going to react this with potassium ethoxide. This is going to make a product. And I want you to set up the Newman projection for this on your own. Just set the Newman projection for this on your own. And what I'll do actually is I'm going to just draw the staggered one. And this is going to be beta. And the carbon attached to alpha is going to be obscured from our view. So we're going to be really looking down the way my pen is pointing. We're going to be looking down this beta alpha bond here. Okay? So what we're going to see attached to beta here are going to be all these groups. What we're going to see attached to alpha here are going to be the groups in the back. I want you to fill these substituents in the reactive conformation where we have this beta and this leaving group anti to one another. And then I want you to not only draw just the generic way you would draw the alkene product for this, but I want you to very, very carefully draw the stereochemistry of what the product is. It's not cis or trans anymore. It's going to be E or Z, since we're going to have a couple different substituents on it. But very, very carefully, is it E? Is it Z? What's the product look like? What's the Newman projection look like? You could also practice drawing the mechanism on here, since this is already expanded, right? Fill in as much of the sheet as you can. In the next 7 or so minutes, we'll return at 10:20.